not a solution of X of L.
No, it is a
No.
solution. Z is a solution.
Oh, Z is a
Example,
solution.
Z is a solution, of course. I mean, that's what the contradiction was.
Is that okay?
Well,
So,
yeah, Z is your U.
sorry?
Z is your U, right?
Z is my U,
Yeah,
exactly.
Z is U, right.
And so,
So,
to
I mean, the whole
simplify,
thing is just
I'm
one
gonna
formula.
write this as sigma
This spelling out some.
alpha. Alright, so I have a formula again, sigma U1, U2, U1, L formula.
B is an X alpha.
Sorry?
Don't you need V?
No. So I've quantified over V.
Oh, so
Yeah.
your bracket
Yeah.
reaches to the end.
Yeah, exactly.
Okay.
Yeah.
Okay.
Alright, so I've got, so that's, this strong linearity reducibility allows me to say that for all V that works. And so what I'm interested in now is few points. Right, point number one, no? And that's the reason I've put it in. Usually I don't, but people don't know why, they ask me why. So if alpha hat in U satisfies, is such that sigma
Just to be careful,
alpha prime T, yeah?
your sigma go all the way to the end of the other bracket.
Yes, and also to the beginning.
That's the whole
Not-
thing.
not just
With
stopping.
the quantifier and everything.
Yeah, you quantify everything, so.
Yeah, but not stopping at alpha 0.
No.
No.
Okay, all right.
It's just your,
Yeah, the bracket
your
is
curly,
long.
your
The
curly
bracket
bracket.
is long.
Did I miss one?
The whole thing.
No.
No,
The under
no,
bracket.
it's
The under
The
bracket.
side that you drew,
The
Yeah.
under
it's
bracket.
halfway through and starts halfway
Yeah.
through and that's what's confusing.
Oh, sorry.
It looks like you mean
And the
the,
other side.
I mean, it looks like you mean the unquantified formula. That's the,
That was lazy.
Oh, look at that. Oh, okay.
Sorry about that. So if we have an element of U that satisfies, then alpha prime has to be in C. So usually I don't write this and people say, why is it? Simply because you can code it in depth, because it's a constant. So, right, so what we have, so are there over alpha hat in C making sigma alpha making this true. Right, so understand maybe the size and so on and so forth.
And T in terms of that, it's just a parameter.
Yeah, T is just a parameter. It's just an element of U with dt equals 1. We fixed that.
Independent.
All right? And so, the first fact,
Making, I can't read it. So making sigma of what's the
UT.
U? Oh, that's a U. Oh, that's a U.
Yeah.
Okay.
Question.
are there. Thank you. All right? So, the fact is that let's denote that as a set alpha in C such that sigma alpha hat T is true. Right? Then we know it's not empty because alpha is one of them. Then we have that C is either C, so then C is either finite or cofinite
Cofinite as a subset of C.
as a subset of C. So cofinite in C, or I just write it
Yeah.
C. Let's see how it is finite. Right. And so for those who know that the constant is already strong liminal, this is not a surprise. But intuitively, we have that C will be, if you want to talk about the constant,
Algebra equal zero or not equal zero.
sorry? Yeah,
You're saying that there's an algebra equation.
exactly.
Zero or not
Yeah,
equal zero.
exactly. It has to be some sort of algebraic equation that's zero, or an equation, or Boolean combination of those. So all right. And so, in particular, right? In particular, as alpha is in C, right? And alpha
Yeah.
is not algebraic. We have that
Oh.
C hat is infinite.
Yes.
But more than infinite, it's actually all,
Oh.
almost all, right?
That'd be
I
cool.
mean, But
That's
the parameter,
infinite.
but
Yeah.
the parameter t is not in QAlg, is it?
No, but
No.
it doesn't affect
It's not really.
it doesn't
That's
affect
the independent variable.
yeah, but it doesn't affect so
Formula.
But you're saying that this set C hat, which is t definable,
It does say
right?
when you
Yeah.
substitute t as well.
So this t definable set is either finite or cofinite.
Yeah.
And now you're saying, okay, you have a generic in it, which is generic over QAlg.
yeah.
But it's not, but it could be algebraic in t as far as you know.
Yeah, but that the T doesn't bring
No, but so
No.
intuitively what you're saying is that for alpha to be in C hat,
Yeah.
it has to be a special property.
yeah.
But it's clear that, for example, alpha equal to T could be a very special
Yeah.
thing.
But it's not going to be a constant.
Alpha equals zero.
It's not going to
Wait.
define the constant. A subset of a constant.
Alpha was
So
equal to
because
a constant, so
C
you
is
can't
stably
put a constant
embedded.
with T because
He
T is
really
not
wants,
constant.
you probably want
T
to
is
say.
stably embedded, so
Alpha
there's
prime is
various
zero.
ways to look at it.
Okay, it's stably embedded, okay,
You
fine.
probably want to say bracket alpha
Yeah.
hat comma
Yeah.
t is in, C cross
No, no,
T.
no. So no. So
No?
the point is that if you think about it, so
Constant.
she gave a few examples. If you think of this, never going to define a subset of a constant. No will things are the form.
Right.
So in Multheory term, we say that C is stably embedded. So all definable subset only requires constant parameters.
Constants.
Just by omega stability.
Yeah, exactly. And you can go further down.
That doesn't tell you that this is.
But alpha prime is zero.
Well, so
It's
C hat
gonna
is
be in the field
defined
of
over
constants.
T possibly, right?
Yes,
Yes.
But now
So it can't be
constant is
T.
stably embedded,
sure.
so T is somehow irrelevant.
But then there are some other parameters which are in C, right?
No, because they have to be parameters that have something to do with T. And T
Yeah,
can't
T
touch
can be,
anything
exactly.
in constants,
Yeah, exactly.
except for algebra.
Yeah, T is
As far as T is concerned,
Yeah.
all the other parameters
Exactly.
of the constants are the same.
yeah, all the same, exactly.
Yeah.
So T is orthogonal.
Oh, okay, T is
T is
Yeah.
definitely orthogonal to the constants.
Constant.
Transcendental constants.
Okay, and so C is cofinite in C, right?
That's right, there are only two choices.
Yep.
It's either one or the other.
Yep.
Or else alpha will have to satisfy will be algebraic.
C hat is cofinite, right? So is it all of C?
No.
No, so
No.
for us,
Oh,
what's
right.
important
You
is
could
I mean,
remove
zero
y.
probably isn't
Oh,
it?
yes, yes,
So-
sorry.
what's important. So for some n in the integers,
Just remove a
Oh.
So for some
variety.
integers, you'll have that
That was amazing.
sigma and
Stuff is
t
magical.
is true. All right. And so that's
Yep.
Okay, wait, but let me.
Why don't you
tell
raise the
them.
right hand
Why is that
side?
the problem?
we'll look at it. So what we say is that is for all v,
N and Z.
if v is in xn,
This is very clever.
then there exists a u not v, and v is in xn. So I'll put it n prime equals 0, and
I think U is in.
sorry,
U
u,
is in.
yeah, u, thank you, and
Yeah.
u v alpha t, right? So
But this violates this unique solution.
exactly, choose v to be the unique rational solution. That's right, a rational
Yeah,
of xn. Then this is saying that you should find another algebraic solution of xn, right? Get a contradiction. Right, because of uniqueness. So, shall I write it a bit more, or?
When you wrote down before that you have a unique rational solution
Yeah.
or unique algebraic,
Yeah.
it was algebraic over C of t.
Yeah,
Okay.
yeah, exactly. So maybe I should spell it out so they exist. So this is saying that there exists a z1 in xn such that z1 is not the same as v. Right, let's choose.
Why?
So the formula is saying
Formula says.
there exists that this is not the same as v. Let's say like you not the same as v,
V.
and f of z1 will be 0. Well, now f will be a polynomial in n, t, y, z, v, v prime, v. All right? And this is saying that z has to be in q, t, arch.
Oh.
Q, T arch, yeah, because V is also in Q, T arch, so everything is in Q. Contradiction. That makes sense? So I've tried to spell a bit more things out, like trying to work with a minimal polynomial. But model theory, we can just use the fact that algebraic closure here is the same as the model theory algebraic closure. So we know that there exists a formula, so we don't have to worry about a lot more things. Okay, so as I say, this is true. This is true for P, same hold for P3, no, sorry, so P2, P5, and P4, right, the Painlevé 2, 5, and 4. But for the Painlevé, third Painlevé equation and the sixth Painlevé equation, there's something that goes wrong. So here, important was that for P1, P2, P3, sorry, not P3, P4, and P5, same thing happened. There is a large discrete set of constant such that there is one algebraic solution. All right? But for P3, we still have a large discrete set of constants where we have algebraic solution, but we don't have only one. We have, sadly, two algebraic solutions.
Yeah.
For P6, we have 12.
Yeah.
Well, not only 12, not only, so in particular we can find a set where there's 12 algebraic solutions. There's many more algebraic solutions than that. But in particular we can find set where they have 2 or 12 algebraic solutions. So the proof still works, but gives something a little bit weaker. An important mole theoretic notion, but still a bit weaker. So let me state the results for if
What does large mean?
large, so infinite. We only need infinite.
Infinite.
Let me put infinite.
Wait, but the parameter spaces are higher dimensional. There you have alphas and betas.
Yeah, so that's why.
Do you
Yeah,
do
infinite.
infinite or do you need zero?
No. So that's the thing. I mean, it needs to be large in the sense that I need to be able to move. I'm able to move one by one parameters, so that I'm able to get into that set. So that's why I put large. So I should put. So, all right. So let me say a little bit more about what I said here. Right. So large, by which I mean. So let's look at P4. So P4 will end up with this formula: alpha, beta, t. Right? So instead of just alpha, so we have two parameters. And the set needs to be such that at first, alpha and beta are independent. So I can move alpha in a set. And then I get a constant here, but beta is still independent from that one. So I'm able to move a beta in such a way that I get into a set where there is one algebraic solution. Okay? And so it's a little bit more involved because you have to study algebraic solution, understand where they have algebraic solutions, try and classify it and put things so that it works for you. But in the end, you are able to.
So in the end, you need something weaker than some students. I mean, that's sort of the
Yeah, you Zariskidens. It is definitely Zariskidens, but yeah, we use something weaker. And so what's the result for P6 and P3? So suppose y1, yk are distinct. Why did I say yk? Distinct solution of generic P3, respectively P6, right? Such that the transcendence degree of this solution over CT are already 2n. Right? Then, for all over solutions, except k, respectively 11k.
You mean K is in?
N?
And k is 11. Thank you. Respectively, and solutions. Solution y for all the solution. Then for all of the solutions.
Oh, you really want to say k and k not equal to n and k not equal to 11n, is that right?
Sorry? No, so I've used n. So I mean I didn't want
That
to.
set or what?
So okay, so that's why I guess I put k initially because I don't want to. So it's not the same n as the one before in a way. So let's put it this way. Maybe that's gonna be
Yeah,
clearer.
there should be k, right? It should be k and then you say k not equal to n and k not equal to 11.
No, not k equals to
Oh,
n.
no, right, there's no
So,
n there.
so as not to confuse with the previous n, although there shouldn't be.
Okay.
I'll take k element and I'll say, then for all of a solution y, except for k or 11k solutions, you have that the transcendence degree of y1 prime yk prime y prime over ct is 2
Solutions.
k plus 1.
I don't know what you're talking about.
No, I don't either.
Why is there y, what you keep and y? Oh, that's a y prime for.
Yeah. So I'm saying, so take k solution,
Right,
and take k solution which are independent,
right.
right? Then for all solution y, except for k many.
Oh, for all k tuples?
No,
for all
k many.
m tuples
For
where
k
m
many
is
y.
unequal to
For
k.
K many y.
K
Yeah.
many y.
No.
No?
For all solution y,
That aren't in that set, or?
except k many. So I will.
You exclude k possible y.
Yeah. All the
All
others
right, all
will
the
have
other
transcendence
ones.
degree. Will be
But
fully
you can make subsets of those. Oh, no, for
No.
all other.
over.
Oh.
So you throw them in the basket and look at what remains.
Yeah. What remains?
And then you,
So I say all of them, except for k many, you'll have algebraic independence. So,
okay, yeah,
right?
yeah, thanks.
That's fine.
All other solutions.
And this is what we call omega category. This is
The transcendence degree. C of t of y1 through y. Wait. For all
All right.
k,
Yeah.
the transcendence degree of those k, those
So if you
whatevers?
start with k of them,
k of them.
then there will be k exceptions
Yeah.
or 11k exceptions.
Or 11k exceptions where you'll have a full transcendence.
That's strange. Because if I start with now k plus 1 of them, then you will say that there will be k plus 1 exceptions. Yeah?
So if I start with
K plus 1.
Of t
Yeah.
equals.
All right?
to-
So let's say I
Yeah.
pick one of the y's which works,
Yeah.
so I have now k plus 1. Right?
Yeah.
Then you say then there are k plus 1 of them, there are exceptions also.
Yeah.
So what's
Because the y
yeah, so,
can
so
add up.
yeah, so what's the meaning of
Well, what's the force of other
wait.
for all other solutions?
No.
So you mean that so I do have k plus 1 of them, which doesn't work, but for that k plus 1 tuple,
Yeah.
and yet for the first k of them, if I put that in, then one of those k plus 1 actually would violate this. No, would satisfy this.
What's the force of
Which
other?
is-
Other.
Other is just for all other solutions.
they
For
can't-
all,
Other-
so
there's a-
for all
other
solutions
y,
that
they should
are
say
not.
y. He should say
Yeah.
y.
So all of a solution y.
Right.
Yeah.
Right. he did.
Yeah.
But, so you can't include that set in that set of, if you had k plus 1, that those y1 through yk are not in that set?
No, it's very
What's
straight.
other
So-
mean?
So you start with, let's say.
Oh, you
let's say
can
start
add
with
to
one.
that set.
Right, let's say, I mean,
I
it's
get it.
something like what I was
Yeah.
hinting
Yeah,
at
I-
very early. So now, so you start with 1y, let's say. All right, so that's equal to 2. And now you say that
Yeah.
for any other y2, right, except possibly
Two.
two of them,
Yeah.
no,
Wait,
one of them.
One
except-
of them.
Yeah.
So there is one exception out there, let's call it z. But other than that z, any other y2
Yeah.
would also satisfy, would give you 4,
Yeah.
right? Any other.
Yeah.
And now you say, now suppose I take y1, y2, then there will be another z, that one is called z1, this is let's say called z2.
Yeah.
No, it will be now called
Why three?
C11 and C12,
Yeah.
right? C11 and C12, which doesn't work, but then the other one, then you will have 6.
Yeah. 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 So
I don't think I get
So-
the force of it.
I don't either.
I don't
Yeah.
think I
Right, so-
get the concept.
so let me write it in a different fashion.
So you know, could you write that down? What just the, from 1, 2 to 3, because I
Yeah,
want to see
that
the
would help.
relationship between the Z1,
Z?
C11
What's
and
Z?
Z12.
Where's Z?
What are the exceptions?
Those
not
are
exceptions.
exceptions. He was just-
Those are the exceptions.
What do you mean by
So,
exceptions?
all right, so say, start with y1.
Start with k equals 1.
Yeah.
Right,
So,
k equals 1.
so we start with y1.
Right, k equals
Such
1.
that
Yeah.
Okay. So
transcendence
now
degree
there
is
is
2K.
there is a Z1.
Yeah. So
There is a Z1
No, no,
which
no.
is bad, which is the
Yeah,
exception.
yeah.
There's a Z1 which is an exception.
yeah.
Z1, such that for
What do
any
you mean by
y2,
exceptions?
for any y2 not
Yeah.
equal to Z1, the transcendent degree will be correct,
Yeah.
right?
Yeah.
Transcendent will be 4. So now we advance to k equals 2.
Right.
Fine, the transcendent is 4. Y1, y2. So
Yeah. Let's put it as differential field. So
Yeah.
Okay, yeah.
Yeah.
Okay, all right. So now that we advance to k equals 2 with y1 and y2, with this particular y2, pick a one y2. So then there exists, let's call it w1, w2. There are 2 of them, there are exceptions.
Yeah.
So that if,
But now if your Y1 is the
Y3
same as the original Y1,
yeah,
is the Z1 being counted as W1?
no, it could be, I don't know.
Yeah.
You don't know.
I don't know, right now, I
exactly.
don't
So
know.
that's yeah.
I don't know.
Yeah, that was
But
the
so,
problem.
so there exists W1, W2 such that if Y3, for all Y3 not equal to W1, W2,
Yeah.
okay, then the degree would be 6.
Yeah.
Okay, so now let's see what happens if I use one of these W1s in the first one. So, since there is only one Z1, one of the W is not Z1, right?
Yeah.
So one of the W, let's say W1.
Yeah.
So W1 is okay.
Yeah.
So in other words, if I put W1 with Y1,
Yeah.
I will have transcendent degree
Yeah.
4.
Yeah.
Would you write that down?
Yeah. So
So say-
y1 and w2 say.
Right, say, okay.
So then we have transcendence degree
4.
4. Yeah.
Okay. And now there are exceptions for this pair.
Yeah.
Now I have to call it what? I don't know. V1,
So
V2.
so
Yeah.
don't forget that there's triviality
Yeah.
behind. So
I see.
at each point, this one is bringing one, this one is bringing
Yeah,
another
right,
one,
right.
So the dependency won't be between, they can't be dependent. It's y2 that brings the dependency here.
Well, no, I want to see if I can bring in Y2 now.
Yeah, all right.
Yeah.
So y1, y2.
Yeah.
problem I had. Yeah.
How do you expand?
Let's see.
Yeah.
No, I should write Y1, W2, Y2.
Oh, w2,
Yeah.
y1, w2.
So let's say there is a V1 and a V2, all right? Such that for all, okay, so maybe instead of Y3.
But here already
No.
the transcendence degree failed.
Why?
Because,
Yeah, because you said
Yeah.
it failed, because it said,
but then it doesn't satisfy.
right, because it says it
Yeah,
failed.
yeah. It's already failed.
Right, it already failed.
I don't understand why
Right,
it failed.
right, right.
Because,
Because of the hypothesis.
W2 is one of the ones you had to eliminate.
I mean, W1, W2 are the bad ones. Since I pick one of them, so it's bad.
So the transcendence degree won't already be,
Bad, right?
we won't
Why
already
is
be
that
full.
bad, that the transcendence?
No, so the
K equals
assumption-
2Ks.
yeah.
K equals 2Ks.
Yeah.
Look,
So
there exists a W1, W2 that are bad.
Mhm.
And I'm using W2 right now with Y1, W2, Y2. So that, therefore, that's bad. That one is bad.
Yeah.
So I can't put back Y2.
Yeah, exactly.
I can't put back
Oh,
Y2.
okay.
Right?
You can put back Y1.
I could put, no, Y1, yeah, Y1 is there, but I can't put
Yeah.
back Y2 and,
And add anything to it and yet
and
maintain transcendence degree. I
I'm
see.
not sure, maybe I could put.
No, but
No, I can't put W1, I
indeed,
put
remember,
W1.
remember
You
that
can.
these Painlevé
Okay, I just
equations,
want to understand what
Yeah.
that's saying. Okay.
Yeah.
Okay.
even these Painlevé equations are trivial as well.
Mhm.
So in any case, it's only enough to consider pair.
Right.
Mhm.
So the
Right.
so,
Oh, that's right.
Yeah,
That's
so-
Right, that's right, that's right.
The pair-
Eventually, you only can.
yeah, so the pair
Yeah.
the pair
That's probably
statement,
the reason why.
the pair,
Only-
pair
Yeah, yeah.
yeah,
That's
exactly,
probably the reason why. you
exactly,
can
yeah,
go on, right?
why you can instead.
Why can't, you don't need the extra.
That's the thing, yeah, exactly. Right, and so this is perhaps a less used notion, well, maybe not at all, but this is what we call omega categoricity.
What is it called?
Omega categoricity,
Oh,
right? So
what is it?
Omega.
So omega
So,
categoricity says what
says that
in general?
in general, it says that if you look at take finitely many elements,
Mhm.
look at the algebraic closure of that.
Right.
So there can only be finitely many of the elements that be algebraic over. So it's a finiteness condition. in the
Ah,
algebraic
finite set.
Mm.
Yeah.
I see. Okay. I see. So that's what you're getting
Yeah.
at here. This is, I'm going to write that down. This is omega categoricity. Aha.
And so one can sort of think about how one can prove that using triviality.
So to
Yeah.
prove this part,
Yeah.
you actually
Very
need
nice.
the particular property of P3 and P6.
Yeah, yeah,
Okay.
yeah. So you somehow will use triviality to only use pairs, right? And again, you'll code everything. You code a sentence alpha, beta, gamma, delta, t. And what that's going to say this time, it's going to say that, let's say this wasn't true. Instead of
Okay, you
K, I
have
had
more.
yeah, I had more. Then you would go down to the algebraic solutions, and you won't be able to find that
Mhm.
one more
Right.
solution. So let's say, let me say exactly.
So the
So this express that for any
Huh.
solution in x3 alpha beta, right? And respectively for x6, there are at least two distinct solutions in K node y, r. So remember, we start with y in our set, and we want to show for contradiction that there aren't more than two elements. So let's code that, say that there are at least two, and then we do the same thing.
Distinct solution. Oh,
why are you
two-
talking about x2 suddenly?
Sorry?
Why are you writing x2 suddenly?
Oh, x3. Yeah.
Ah, okay.
3, yeah.
Sorry.
And that's supposed to be K naught Y, Y prime?
Or at least
So-
2.
Yeah,
K
K
naught
naught
y
y.
prime. Thank you. Writing things too fast. And remember, K node now is the appropriate F node with the appropriate parameters. So the idea is we express that in a sentence, and then we move the parameter appropriately in a set where there's only one algebraic solution. So this sentence says that we will be able to find another solution algebraic, which is not the case. So we can't have two. So we can only have one more in the algebraic closure.
K naught was C of T, right?
A K node was, in this
Yeah,
case,
K
would
naught
be
is
Q
Q of
alpha.
Oh,
ah, right,
beta,
parameter and then T. Yeah.
oh, okay. Yeah. So instead of, for notational economy, instead of writing y prime, you can write K
The
naught. It's the differential
Yeah, yeah,
field
yeah.
generated by y, at least.
Yeah, because y double prime is
Yeah.
there.
Yeah,
Exactly.
just to save writing.
Well, no, but it's easier to see that the transcendent degree is 2 times that.
That's
Yeah,
true.
yeah,
That's
yeah,
true. When
yeah.
you spell it out,
And also, I mean,
Yeah.
I knew there would be some model theory, so I don't know
Oh,
if
that's
they
true.
know
Right,
the
right, right.
implementation.
that no, that they
Now,
wouldn't.
There's a
Yeah.
question here.
Yeah.
Now, you mentioned earlier that for Painlevé 6, I suppose,
Yeah.
right?
Yeah.
Then you can find 12, some of the other solutions.
Yeah.
Algebraic solutions, called algebraic solutions,
Yeah.
right? And you subtract 1, and that's why you get
Yeah.
11k, is that right?
Yeah.
Why?
So,
four?
so think about, as I say, triviality.
Oh, that's
you
the
only
11.
prove. You need to prove for 1 for
Ah.
triviality,
Yeah.
I
right?
see.
So it's going to be 11, right?
Yeah.
Now,
Yeah, that's-
but you also said that, well, maybe there are more than 12 algebraic solutions, right?
Yeah.
What if you now find 13 of them? Would you have to change that number?
No. So this is actually, so we haven't, this is not sharp saying that it's not strictly disintegrated, but we can't prove a full transcendence. What we have now is a sort of lower
you
bound.
said you accept
Just K and 11K.
only 11 of them, right?
Yeah.
Okay, start with K equals 1.
Yeah.
You only, but now if you find 13 solutions,
Yeah. No,
then
but
how
No,
you
so
know,
remember-
excluding only 11
For-
would work.
for the generic, there are no algebraic solutions. So we're talking about the generic case size. So we don't have algebraic solution at all. So our proof
The
uses
proof
a trick.
forced it
yeah,
into-
forced it
Yeah.
into.
To the
Yes.
algebraic
Yeah.
by contradiction,
Yeah.
so it doesn't
To
happen.
Z.
Yeah, yeah, exactly.
Yeah, that's why
Yeah.
N was there.
It's strange.
It went to Z.
It's like Fermat's theorem. Last theorem, right?
Yeah.
Things don't exist really, and you prove a whole lot of things which doesn't exist. Okay.
All right, I think.
Thank you very
No,
much.
sorry, I shouldn't end it.
Very good, thank you. Very good.
Beautiful lecture, beautiful lecture.
How do you get down to the precise statement that generic in P2 means not in 1/2 plus Z?
So the question is, how do I show?
How do you get it down to, for all alpha,
For
not
all,
in 1/2
you have geometric
plus
triviality.
Z? You have, yeah, geometric
So-
triviality.
So you want. So newest result is that for all
Yeah,
for alpha not in 1/2 plus z,
right.
x alpha, so x to alpha, is geometrically trivial.
Right.
All right. So we use the so how we use the trichotomy. I kind of use the trichotomy in some way. So first, I try to generalize. So remember Nishioka had proven for P1, right? And so he uses the fact that the equation is very simple and try to do differential algebra. So if you try that with the second Painlevé equation, that doesn't work. There's
Well.
things. But what I could somehow prove, I could get down to, was the following. So let's put it like that. So let y, so we take alpha in not in 1/2 plus z, right? So alpha not in 1/2 plus z. So let y let yz be in x alpha, distinct, right? If let's say if z is in k y prime alg, then so any, and let k be any extension
Oh,
of ct or qt q alpha t.
of C of T, yeah.
Then, if z is algebraic, then z, it's because that z is actually rational
Yeah,
over y prime. So, another way of saying that, there are no finite correspondences. Well, I should say. So I must say one thing. I have to correct one thing. I need this thing But I also need generic, by which I mean it shouldn't be algebraic. So where y, z are not indicate algebra, right? So I take generic solutions of a Painlevé equation. So
Oh, okay.
Doesn't satisfy.
over than bijection.
Y prime, okay, Y prime not
Right? So we can't find finite.
Sandwich?
Yeah.
Can I eat my sandwich?
Yeah, of course. So there's no generic finite
Actually,
correspondences. Yeah.
It's not just YZ not in K algebra, but rather they should not be algebra dependent over K. I mean, one of Y could be transcendental over K, but then Z could be algebraic over Y, that won't work.
No, so what I want is I want to take two distinct solutions which are not algebraic over
Yeah,
K.
but suppose I take one Y, which is transcendental, all right?
Yeah.
But then I take Z, which is algebraic on Y.
Yeah.
It will satisfy that condition.
Yes. So that's the point. The point is that I am talking about a property of generic element. So I'm not saying that it doesn't hold if you take algebraic. What I'm saying is
Okay.
of generic element, that's a property.
So Y and Z both transcendental, but
Yeah.
they could have algebraic
In
relation.
Putin, yeah.
They could have,
Yeah,
okay.
yeah. But what I show is that if
But then
they
if
do,
that's the case, then it would fail, right?
it would fail, exactly. So what I'm trying to show here is that if they are algebraic, actually, then they must be
Oh, okay, okay.
Yeah.
there should be rational.
It's like Jerry and Alice's proof for P1.
Yeah, exactly. Exactly.
Oh, yeah.
And so what I'm saying is there's no generic correspondences over generic
What does
binomials.
that mean? There are no generic
So a
correspondences?
finite,
But what the nature of the map?
differential rational.
Oh, differential rational.
So basically, so if you can think of
So you're thinking in
So
a
F-
differential
yeah.
algebraic geometry.
yeah, exactly,
Okay.
exactly in differential algebraic geometry, exactly. So generic that context. So why is this important? It's important because let's look at EA sharp or E sharp. On the other side, look at take an elliptic curve. Look at multiplication by n map.
Doing here.
Right? So this is a n squared to 1 map. So it's a, in a way, finite correspondence. And so, by the way, how we construct E sharp, which is the Cauchy closure of the torsion point, we also have this as well.
Excuse me, I missed your
Yeah.
multiply by n, is that right?
No, multiplication by n.
Oh, multiplied by minus n?
Minus n or n?
No,
No.
so
Okay, multiplication by n.
yeah, so this
Multiplication by n.
Mult-
Oh, wow.
by n. So I should just let's try.
Consider bracket n
Yeah.
mapping E to E. Oh, E sharp to E sharp?
Yeah.
Oh, E to E. I'm way behind with E. My sandwich.
So we're E elliptic curve.
N squared to 1.
So this is an example. So this is a finite, a correspondence. Say. That's not the move bijection, right?
E sharp is also an n squared to 1 map. Unequal to pi. So are you using the fact that E sharp consists just of the torsion group, Or you don't care?
No, so the fact that it's Zariski dense in E and that it fully contains the torsion group. So you always have, you can show that the
But E sharp is just the torsion group,
E sharp.
in the differential closure of C of T at least.
So that's for,
That's
yes,
for-
in the differential
yes,
closure,
yeah.
but we're looking in
You're
our
looking
big
at
U.
any,
Yeah, so,
okay.
So, sorry,
Yeah, yeah,
we're
yeah.
working, still
Yeah,
working
yeah, sure. So you have to close it up.
You should still working in our big U. And so why is that important? So the next question is,
Right.
so remember the trichotomy turns out to be a dichotomy for the Painlevé equation. So if it was not geometrically trivial, then it would have to be non-orthogonal to the Manning kernel, right? So let's say X alpha strongly minimal implies that this doesn't happen, this happens,
Right.
this happens, right? Or geometrically view. So either of these two. So the question is, do these correspondences, are they kind of preserved under non-orthogonality?
Right.
Because if they are preserved under non-orthogonality, then the Painlevé equation can't be non-orthogonal to the Manning kernel. Because on one side you have something that can't have any correspondences of bijection, but then on the other side you'll have things that can have.
Could you go back over that? I didn't quite. So what are you supposing? Suppose it's
X alpha-
strongly minimal.
No,
Strongly minimal would
Yeah, so X
specialize
alpha
in
is strongly minimal,
But
implies.
implies.
Bring it down to 2.
Yeah, it brings it down.
Let alpha be strongly minimal, then one is not true.
one doesn't work because it's of order 2. So X alpha, remember that's the Painlevé equation, right?
Right.
So it's of order 2.
Then right. 1. X is not orthogonal to C. Okay. 2. X is not orthogonal to E sharp Y.
No. So,
You don't know that. Okay.
Yeah, so we don't know
You didn't
that.
cross it out yet.
Right?
Gotta uncross it.
So to cross this out, all we need to show is, so the next result is that.
Okay. So you want to cross out 2?
Yeah. So let X be
Geometrically trivial.
be strongly minimal. Let's say order 2.
Right.
Right? If
Order
X
2.
is non-orthogonal to E sharp
Yeah.
for some E, not defined with a constant. So if it's not, then
It all fell out. Oh no.
there exists a K. So K can't be, so there is K here, that may be confusion, but let's say F, because I used K to be CT before. Then there exists F, extension, differential extension
Strongly minimal order 2. Let.
of CT, okay, such that
X is
there are correspondences that are not bijection, right? So over a differential field F, there exists.
When you're taking notes, it just throws you back.
That's fine.
Then there-
There exists
Right.
YZ
F differential extension.
in X,
See if X is
YZ not in F ouch, such that exactly the opposite of that one. Z is in F, Y, Y prime ouch, but not Y, Y prime.
Says Y, Z, X, Y, Z, not in F, algebraic, with Z in F
Right, so this is, again, this uses model theory, and you just show that the multiplication by n map does kind of carry through non-orthogonality. So you would have things that are interalgebraic, but that aren't interdefinable. So you would have exactly correspondences that are not bijection. And from there you get directly that the second Painlevé is geometrically trivial. Because for the Painlevé equation, over any field extension, if you take two elements that are not algebraic, you'll always have that, if they are algebraic, they are
Rational, yeah.
rational. So this contradicts that.
But aren't you saying the results? Oh, the result.
So let X be strongly minimal set of order 2. I'm not saying
And
X
you're
is
assuming it's not orthogonal.
non-orthogonal to E sharp.
E sharp.
If it's non-orthogonal to E sharp, then you will find F a differential extension.
It's trying to force it geometrically.
Yeah.
But aren't you trying to eliminate two?
Yes, so that eliminates 2.
Yeah, so you have some contradiction.
Oh, yeah.
Yes.
Because so it's either this, so if x2 was non-orthogonal to the Manning kernel, then this should hold.
Oh, I see. If two
But
held,
this contradicts
then
this one.
right, that's not orthogonal.
Yeah.
Right. To E sharp, then there would exist F, and in Y and Z and X, such that Y and Z is not algebraic.
Yeah, it's not rational. You just say that it's not rational, right?
Yeah.
It is. Could you give me a model theoretic definition of geometry trivial?
Yeah, if you understand algebraic closure, it's very easy. So let X be strongly minimal set, right? So let's call. So do you know the algebraic closure operator in model theory?
I suppose.
So let's say for a subset of X, for a subset of X, right? You will say ACL X of A is simply the algebraic closure in model theory sense of A intersect X. Right, so I localize X inside. And so X is geometrically trivial if for all A, the algebraic closure A is the union A and A of the algebraic closure of A.
What does the right-hand side mean, that last thing that you wrote?
This one?
Yeah.
Oh, sorry. Thank you.
Okay, that makes a little more sense. Oh, okay.
And so why do we talk about binary? So if why do we talk about binary? So simply if we take y1 to yn, right, in x, and we look at ACL x of y1 to yn, and let's say that z is in there, but if it's geometrically trivial, this is a union of I of ACL x of the yi. So if it's in a union, so z is already in one of the algebraic closures. So it's unindependent. Yeah. So that's how we translate from. Yeah. So if there's
Where else does this property, geometric triviality, happen naturally in some sense?
so it's somehow it's a bit an exciting time. So the J function satisfy a different third order differential equation as well.
Mm-hmm.
So it's been long believed that any geometrically trivial set is omega categorical. Do you remember this omega categorical finiteness of algebraic closure? So recently, James and Tom Scanlon, proved that the equation satisfied by the J function is geometrically trivial. All right? And what are the example of binary structures there? But they're not omega categorical. Example of binary structures are so if let's call this equation chi equals 0. So that's the third order equation that the J function satisfies, right? So all solution of these equations are of the form J tau for J in GL2C. Right? So that's solutions, right? So, right, if you start more theoretically by a big differential field, use the embedding theorem, you can realize solutions as that, all right? And so if you have dependencies, if AC, L, J tau, J1, and J2 tau. Sorry. I mean, if J1 tau is in ACL, J2 tau, right?
Okay.
What can it be? Well, it can only be modular polynomials relating. Relating the two. And this is example of a geometrical trivial set. So it's known that the only relation that will come from modular relation. But this is not omega categorical, because for each n, solutions.
G is linear fractional?
Yeah, linear fractional.
I wonder. Stupid. Yeah, right. G and GL2 acting as PGL2. Let's see, go back over that again.
Yeah.
I was puzzling out.
So I'm saying this is the third order differential equation satisfied by the
Yes.
function. So one can always realize, if you want, the solution as the J function with
Fractional transform.
a fractional transformation on
One variable.
the variable.
Oh, it
Right.
must have to do with the Schwarzian derivative?
Yes.
Yeah,
exactly.
okay.
Yeah.
Oh, get it.
And
Yeah.
what's known is that if they are interalgebraic, right, then it boils down to modular polynomials.
Right.
So,
And remind me what that is?
so the modular polynomials. So how can
I
we
see this. Oh no, that's the first time I see. Yes, I see. That's the significance over algebraic over one of them.
Yeah.
Oh.
Exactly. Yeah, exactly.
A little
Exactly.
slow.
No. That's perfectly
Oh,
fine.
so what are they again? I could look it up.
So the exact definition is
Sort of
But
vaguely.
generally
what are they?
speaking, we don't really care what that equation is.
What?
I mean, for the
Which
geometry-
equation?
For the geometry,
geometrical.
For the modular.
Yeah, exactly.
We don't
So-
really, but for the J function,
Yeah.
we know what those are,
Yeah,
what
yeah.
those equations are. That's all I'm saying.
Yeah, exactly.
So,
So-
that's an example of this kind of.
Well, what did Jim and Tom pick?
So they show. So usually we have the conjecture was that there's finiteness of an algebraic closure. Which
Right,
if you start
right.
with an element,
That's
there can-
omega categorical.
Yeah, there can only be finite.